Which of the following would react faster than benzene in an electrophilic aromatic substitution reaction, otherwise known as an EAS reaction? So what we need to do is we need to take a look at the general mechanism for an EAS reaction to see what role the benzene is playing, if it is the electrophile or the nucleophile in the reaction. So if we're looking at an EAS reaction, so you can use benzene or substituted benzene or another aromatic compound. And so you're going to react to this with an electrophile. So I'm just going to write a generalized electrophile. And so what happens in the first step is that your pi electrons of the benzene ring act as a nucleophile. So this is going to be important to answering this question, is understanding that the benzene ring is the nucleophile. And so let's go ahead and draw the rest of this mechanism. Even though we've got the piece we need to answer this question, let's go ahead and draw the whole thing. So what we have done is we have formed a new bond to that electrophile, whatever it is, and both carbon atoms here, actually every carbon atom of that benzene also has a hydrogen. So I'm going to draw in the hydrogens just around where we did that reaction. So we'll see that now we have this sp3 hybridized carbon, and your other carbon of that pi bond is your carbocation. And so this is similar to what we saw with alkenes reacting with electrophiles. The difference here is going to be that instead of a nucleophile coming in and adding to that positive charge, we're going to remove the proton because that's going to make our aromatic ring reform. So you'll have some generic base in solution. So I'm just going to put B minus, or just B with some electrons actually. And this is going to vary depending on the actual EAS reaction. And so where this is going to remove the hydrogen is where you added your electrophile. So that's why it's a substitution. You're substituting a hydrogen for an electrophile overall. So then these electrons are going to come in to reform your aromatic ring. And so that's the general mechanism for an EAS reaction. And so this is a reaction with benzene. What we're looking at here is what happens when you substitute benzene. So we're looking for something that's going to react faster, which means we're looking for something that is a more powerful nucleophile, so more nucleophilic. So this will happen if you've added a substituent to the ring that is electron donating. So that's really what we're looking at. We're going to look and classify all of these substituents as to whether or not they're electron donating, which would mean it's going to be more nucleophilic and go faster, or electron withdrawing, which would make it go slower. Okay, so it can be, you can have electron donation through either like an inductive effect or a hyperconjugation from an alkyl group, say. So alkyl groups are where we really see this inductive electron donation. Or you could have it through resonance if you had a lone pair of electrons that could effectively resonate with the ring. So if we look at the first one here, A, we have an alkyl group. And we just said this is one way that you can donate electrons via induction. So this substituted benzene ring would react faster than just an unsubstituted benzene in an EAS reaction. So with that, we've got the answer to the question, but I think we should look at all the rest of the substituents. So if we look at B here, this nitro group, we should draw out the structure of the nitro group so that we don't mistakenly think that there's a lone pair of electrons on the nitrogen. So when we draw this, we're going to see we have a double bond to one oxygen and a single bond to the other, which actually puts a positive charge on the nitrogen. And of course, you can draw the resonance within your nitro group. So you could have the double bond here and the single bond here. It doesn't matter. So this is actually a very, very powerful electron withdrawing group because it can withdraw electrons through resonance. So this nitro group is electron withdrawing. So that means that this would go slower than benzene. It is less nucleophilic because we're pulling electrons out of the ring. And we have the same sort of thing for C because we can pull electrons out by resonance into that carbonyl. So this is also electron withdrawing. So this will also react slower. So these are both electron withdrawing by resonance. And if we get to D, you do have lone pairs of electrons on your halogen, on bromine. However, you do not have good overlap between these electrons and the p orbitals of the ring. So if you think of where bromine is on the periodic table, its outer shell of electrons is in just so much larger of an orbital that you're not going to have effective resonance. So these don't overlap effectively. So we don't have resonance here effectively. Sorry. So you don't have resonance. What you have is a slight electron withdrawing through induction. So this is electron withdrawing. Through induction. So this would also react slower. And so that'll be true for all of your halogens. So fluorine, you might think, well, it's also in the same row as carbon, so maybe you could have effective overlap, but it's so electron withdrawing. It's your most electronegative atom on the table that even fluorine is electron withdrawing. So all of your halogens are electron withdrawing through induction and will react slower than just benzene in an EAS reaction.